First we're going to talk about vector projection, and then we talk about scalar projection. So what is a vector projection? The notation would be like this. We're going to write projection of vector B on A. Now, even though I did not mark A as a vector, we understand that it's a vector. So both of them are vector. Yeah, go ahead.
Just review, because you know you did this.
Yeah, I said that this is the projection of, or the projection of B, of vector B on A, on vector A. So if the two vectors are like that, and if we drop a perpendicular from the top, the endpoint of vector B on vector A, here we have 90 degrees, this portion is the projection. Okay, so, and this is the projection of a vector is a vector, but scale. Okay, and we have a scalar projection, which is the magnitude of the vector projection. And the notation will be comp B on A, like so. It's the sine magnitude of the vector projection. Now, why sine magnitude? I mentioned that last time. The magnitude is always positive, a positive quantity, but because this projection can be can apply to a case where we have an obtuse angle between the two vectors, like so. Then the projection of B on A will be on an extension of A in the opposite direction, like so. So this part will be the projection of B on A, but you can see that the direction is the opposite. So the magnitude in this case will assign it, will give it a negative sign. To calculate the scalar projection, we have a formula for it, and you can see from this picture that if this is theta, the angle between the two vectors, then the magnitude of the red or of the projection is simply B cosine theta. So we're going to say that comp B on A is simply the magnitude of B times cosine theta. I think this is the where I'm going to take off on this one. You can see that a note that I made last time that the scalar projection of B on A is negative if theta is an angle greater than pi over 2 and less or equal pi, as the cosine of an obtuse angle is negative. Using the dot product, we can derive an expression for the scalar projection. And so if you recall that the dot product gives you the following. So recall that A dot B equals the product of the magnitudes of the magnitude of A times the magnitude of B cosine theta. So you can see that if you divide this expression by the magnitude of A, then we get the following. The scalar projection of B on A will be simply the dot product divided by the magnitude of A. Okay, we can write it like so. But what is the magnitude? What is A divided by its magnitude? It's a unit vector correspond to A. So we also can write it as, and the unit vector, so it is this vector. The unit vector is still a vector. So we can say this is the unit vector correspond to A dot product of vector B. Okay, so that's another way to calculate. If you don't know the angle, for instance, and you don't want to go through calculating the angle, then calculate just the unit vector and dot product it with the vector you want to project. And this will give you the, so let's write it in. So it's equals to unit vector of A dot product B. Okay, makes sense? So how this apply to the projection on of a vector B on A? Well, we're going to write that the projection of B on A going to equal to the following. It's equal to we're going to take the size of the projection is the magnitude, right? Is this quantity. So the size of the projection of the vector, that is the projection, is the scalar projection multiplied by the unit vector in that direction. Does it make sense? And the unit vector is always in the same direction of the vector, and the projection is a vector itself. So in the scalar projection is its magnitude. So we're going to write it's the scalar projection which is comp B on A. Let's see, comp B on A, we said it's the dot product. I'll use this expression right there. It's the dot A dot B divided by the magnitude of A, like so. Okay, so this quantity is simply comp B on A, and then we're going to dot product it with the unit vector in the direction of A, because after all, the projection of B on A is the same as the same direction. So we have this expression. If you look at it very carefully, we can write it as A dot B. Here we have the product of the magnitude, so we have the magnitude squared, right? So, and then right now, what do we have? This quantity is a scalar. The dot product is a scalar, and the square of the magnitude is a scalar. So this is just a number. It's no longer a vector. Okay? And so it will be a scalar multiplier of the vector A. This is not a dot product. Again, this quantity is just a scalar.
So on the left side of that equation, that's not a dot product, that's a multiplication between the...
This is a dot product, but the result of the dot product is a scalar.
Just an inch to the left.
This is just a scalar multiplier of the vector A, which makes sense.
Right.
Because that's the projection of B on A.
On the other side of the equation, just before that?
This one?
No.
The term in the middle?
In the middle, in between, just after the right-hand parenthesis.
Is it a dot?
Yeah, that.
This is a dot.
No, not that one.
This one is a dot as well, because this is a vector. No, this is not a dot. This is still, you're right, Ben. This is not
Yep.
dot product. This is a scalar,
Okay.
and this is a vector, but this is not a vector. So, likewise, okay, like so. So we can write it, we can put parentheses right here. Again, scalar multiply by vector. All right, I think we're good for an example here. I have it as example 6. So we want to find both the scalar and the vector projection of a certain vector. So find the scalar and vector projection of A. This is the vector 1, 1, 2 on vector B, which is negative 2, 3, and 1. Okay, the solution on the next page. So here comes the solution. So essentially we need to find the dot product, and we need also the magnitude of A. So we can do it in one shot, I think. Let's find the scalar projection. So comp B on A. So remember we had, it's a dot product, it's A dot B divided by the magnitude of A. Am I done with the split?
Even though you said A on B, you're still going to write B on A?
I'm sorry, did I say B on A?
In the example,
Yeah, thank you so much. Let me bring it back. Let me undo the split. So let's rephrase the question.
so it does matter.
Let me. It's B on A. We want. You know what? We'll change it to A on B. It's easier to do it than change the whole question. I hope it won't confuse you, because the notation will be different. Because now we're going to do projection of A on B. I'm sorry?
Gold Star Live.
I know. That's pretty good. This is a keen observation. So we'll do projection of A on B. Okay. So let's see the two vectors. So the dot product will be 1 times negative 2 plus 1 times 3 plus 2 times 1. And the magnitude will be of B in this case, the bit square root of negative 2 squared plus 3 squared plus 1 squared, like so. So remember, this is the scalar projection, so the result should be supposed to be a scalar. Let's see what it comes out to. So we have negative 2 plus 3, so that's 1 plus 2. So we have 3 on top. Actually, I have room to write it here. And this will be 4, 9, 13 plus 1, so the square root of 14. Okay, we got that part. Okay, make sure that it's correct.
So, okay, we're good.
No objection? All right, the projection is of A on B will be the comp times the unit vector correspond to B. So it will be the scalar projection of A on B multiplied by the unit vector, so it's B over the magnitude of B, like so. Okay. So it will be, well, the magnitude of B is square root of 14, so it will be 3 square root of 14, like so, and then the unit vector will be -2. You can write it as -2, 3, and 1 divided by also square root of 14, like so.
Isn't that B that you just took?
I need to do B. The absolute.
The unit vector would be B in this case? Oh, yeah, I'm sorry. You're right.
Yeah, it's B over A. If it's A over B, it will be the unit vector of B. Go ahead,
Why
James.
is the magnitude 3 over 14 and I square root of 14 not just?
This is not the magnitude. This is scalar. This is the scalar projection.
Oh, okay.
This we got it from here.
I
See?
see what you did now.
Yeah, and then this will be the unit vector of B, corresponding to B. So now we can simplify it. It will be 3 over 14 times all of that. So if we break it down, it will be -6 over 14. Of course, we can reduce it, so we can write it first 1 over 14. This will be the scalar, and then we multiply it, so we have -6, we have 9, and we have 3, and we can leave it at that, or if you want, if you really want to write it, then it will be 6 over 14, -6 over 14.